Long before anyone understood germ theory, humanity was fighting an invisible war against decay. The ancient Egyptians knew that to preserve tissue for the afterlife, they had to arrest the natural process of decomposition. For centuries, our medical interventions were acts of desperation. We poured raw, burning alcohol into open wounds, or packed them with caustic substances because they were the only harsh things we had at hand. When an epidemic hit, we turned to our universally lethal weapon, extreme heat. A roaring bonfire rapidly obliterates any pathogen it touches. But incineration has a severe operational flaw. It destroys the terrain along with the enemy. You cannot toss a patient, a delicate surgical instrument, or an entire city's water supply into a furnace to save it. Survival required a more precise strategy, finding a way to selectively assassinate microscopic invaders while leaving the complex macroscopic world completely intact. This diagram illustrates the strict set of chemical rules dictated entirely by the terrain we want to clean. If the surface is a living human arm, we use an antiseptic, a chemical mild enough to leave healthy tissue unharmed. If the surface is a lifeless steel surgical table, we deploy a heavier chemical, known as a disinfectant. Crossing these two categories carries a high cost. Applying a heavy industrial disinfectant to a human patient will indiscriminately strip away and destroy living cells alongside the targeted bacteria. Everyday hand soap functions as a mechanical surfactant, a compound that lowers the surface tension of water, allowing it to grab hold of oils and physically wash threats down the drain rather than killing them directly. This visualization shows what happens when we use a solution like rubbing alcohol to actively kill pathogens. The alcohol requires water to act as a catalyst, allowing the molecules to enter the bacteria and denature, or unravel, the complex knotted protein structures that keep the cell alive. Hydrogen peroxide attacks through oxidation, ripping electrons away from the cell walls of an invader. When poured into a deep, oxygen-starved wound, it reacts with an enzyme in our blood to rapidly release oxygen gas, creating a bubbling effect that physically pushes debris to the surface. The cleaning solutions under your sink function as a highly targeted armory, engineered to safeguard the fragile biological terrain of our daily lives. Treating an individual body requires one set of tools, but scaling protection to a massive flowing environment demands a completely different approach. Securing a city's water supply means deploying a chemical that can neutralize threats across millions of gallons without poisoning the population. For this, we rely on halogens, specifically chlorine. In tiny, highly regulated doses, chlorine disrupts the enzymes of waterborne pathogens efficiently and cheaply, scaling up to handle the immense volume of modern infrastructure. Then there is the historically deadly terrain of the operating room. In the 19th century, Joseph Lister set out to stop the rampant infections that made open surgery nearly a guaranteed death sentence. Lister deployed phenols, specifically carbolic acid. Using a mechanical sprayer, he created a continuous chemical mist over the patient, allowing the acid to instantly denature bacterial proteins before they could settle into the exposed tissue. By maintaining this constant chemical barrier in the air, surgeons could safely bypass the human body's first line of defense, the skin, without inviting mass infection. Similar chemical logic applies to heavy metals like copper and silver. They bind tightly to proteins to shut down cellular function, a reaction we still rely on today to manage specific municipal pools and protect delicate environments like neonatal care wards. Scaling these reactions allowed humanity to conquer the massive footprint of modern cities and survive the severe vulnerability of open surgery. Certain terrains are completely untouchable. We rely on highly complex medical endoscopes and intricate planetary rovers, equipment that would instantly melt under extreme heat or short-circuit if submerged in liquid disinfectants. To sterilize sensitive medical plastics, hospitals turn to glutaraldehyde. This compound cross-links proteins in a way that rigidly paralyzes and kills bacteria, all while leaving the delicate plastic tubing perfectly intact. The stakes peak when we send equipment into the vacuum of space. We must ensure we aren't seeding a neighboring planet with Earth-borne bacteria hidden deep inside the wiring. For this, technicians deploy extreme, highly toxic gases like ethylene oxide. The gas permeates microscopic crevices within complex electronics, aggressively shredding the DNA of any lingering microbes without leaving behind a single drop of moisture. When a surface is too intricate for mechanics and too sensitive for fluids, we saturate it with lethal vapor to achieve absolute biological neutrality. We have evolved far past the indiscriminate destruction of fire. Instead of burning down the environment to kill the pest, we've spent centuries mapping the exact molecular vulnerabilities of our microscopic enemies. Every time you wipe down a kitchen counter or wash your hands, you are actively deploying this highly specific, historically hard-won chemical weaponry. Modern cleanliness depends on an invisible, precisely engineered microscopic battlefield that neutralizes splats beyond the reach of physical scrubbing. This calibrated chemical shield is the fundamental technology that makes modern medicine, safe urban living, and interplanetary exploration possible.